My name is Bob Cowan. I'm the host and moderator for you new guys. Welcome. We've got a very interesting program today. Before I get into Kristen, I want to make a quick advertisement, if I might. For those of you who are new here or for the first time, if you want to be told about what the next presentations are going month to month, if you'll go to Groups.io and sign up on new Yaseu Zoomers, you'll get a notice every Sunday with the upcoming discussion groups. I'm delighted to introduce our guest speaker today, Kristen McIntyre, K6WX. Kristen is an accomplished electronic engineer and an MIT graduate, and she currently serves as the first vice president of the ARRL. With her deep technical knowledge and passion for innovation in amateur radio, she'll be sharing insights on long wire antennas, a fascinating and practical topic for us all. Kristen, it's all yours. Take as much time as you need.
Okay. Yeah, well, it'll be kind of antennas in general, as opposed to just long wire. So let me bring up my screen share here.
And should anybody have a question while she's making her presentation, raise your hand and Kristen will recognize you.
Absolutely. Absolutely. And if I miss somebody, just let me know. So what I'm going to talk about here is, a subject of interest to all hands, which is antennas. And one thing about antennas is everybody's got their fave, and they are kind of anecdotally evaluated amongst various people most of the time. But I want to give you a little bit of theory backing first, and then talk a little bit about some specific cases so that you can get an idea of what you want to look at when you're thinking about one antenna versus another, or even trying to choose one for a particular situation. So for a lot of people, antennas are just these mysterious devices. They're made of metal, but they seem to involve some kind of geometry. And they have characteristics that can vary based on, where you put them and how high they are and this and that. But some of it we can calculate, and some of it is just really hard to calculate. But some of them are easy, and I'm hoping that by the end here we can boil this down into a few simple characteristics that you can use to evaluate what's going on with an antenna you're interested in. So we're going to try and demystify this a little bit. We're not going to care about everything about an antenna because that's a lot of work. There's lots of important things and lots of things, and we want to tease the important things out of the things. And you'll find out that also a lot of antennas are just variants of other antennas. There's a few basic types, and most of the other ones are just like that, only slightly different. And then you can find out how to optimize the things that really matter as opposed to over-optimizing things that don't. So if we start with the basics, we have some really simple structures and some simple models. And we're going to look at those and figure out what we want out of those, evaluate that, and figure out, more importantly, where the power goes, because that's what matters in the end. You're trying to get a little bit of energy from your transmitter up to somebody's receiver, and you want to make sure that that's done in the most efficient way that you can do it easily. So there's a bunch of calculations one can do to calculate dipoles. It comes with a bunch of assumptions because the actual field calculations are complicated, especially in the near field. And we can use a finite element like analysis to get down in the mud there. But to just get some basic characteristics, we can use what's called the far field assumption, which means you're out a wavelength or two, and then calculate field strength from that. It's still a bit of a pain. Here's a sort of a animated view of what's going on, and some of the assumptions are implicit in this diagram or animation, where you can see the voltage varying and going to kind of zero right at the feed point at times, which it does do, but you see the current maximizing and minimizing too. And it's not exactly sinusoidal, but close enough for government work.
Is everybody seeing this? Because I'm still on the first slide. Sorry to interrupt.
Oh. there's is everybody seeing something that says coupling to space-time?
Somebody else just put in the chat that they only see the title slide as well, so it's not just me.
Really? Oh, goodness. Well, let me see what we can do here.
I've still got a wire in the air, what matters most.
Yeah, that's
okay, thank
odd.
you. Yeah.
Does that clear it up?
Yeah,
Okay,
I can see the other slide
good.
now, but you're not in presentation mode.
Yeah, exactly. So I don't know what to do other than usually this. Oh, I know what. I know what will fix this. Hold on one sec. I've seen this before. Just share the whole schmear. I think that does the trick. Okay. And then that.
Coupling to space-time, that's what we have.
Yeah, there we go.
That's
So let me
right.
go back to the end. Let me go back a slide and see if that works. Okay, you see dipole calculation? Yes,
Yeah,
no?
that's all working now.
Okay, awesome. Okay, so I'll show you that animation again because it's kind of amusing to look at. So you can maybe see that happening with the voltage and the current. And like I said, that's not an entirely accurate representation. So what we have to do is we have this voltage and we have current and we have a piece of wire and we have to get this thing into space-time and so that it will propagate using the wave equations. And the wave equations show us a little bit about how propagation happens. That's that del squared E del squared H there. That's called a Laplacian, and that shows us a spherical propagation from a point source. But if we, calculate, we find out that and this has to do with the permittivity and the permeability, electrical permittivity and magnetic permeability of free space. We find this thing you've probably heard, 377 ohms, which is approximately 120 pi, is the space-time impedance. Now, one of the interesting things about this, and I'm going to dig into this a little more, is that when things move away from your antenna or from whatever's putting energy into space-time, it appears dissipative, even though it's not really dissipating energy. So in other words, it looks resistive. And so the energy gets put into space-time, but when we calculate things, they look like resistors, believe it or not. So the interesting question here is, where does all this energy go? And what you're seeing here is a representation of what's called the pointing field. And so the energy itself is in the fields. That's a deeply mysterious topic in itself. We kind of have a quantum field theory that tells us how the energy kind of gets through space-time, but again, that's just a mathematical theory that gives us a lot of good results, but we don't know physically what's going on, except to say that we have these fields, they move through space, the speed of light, which is related to that magnetic permeability and permittivity of the electric field, and but we don't know what exactly in physical space is being tweaked by that. And then we ask questions like, what leaves and what comes back? And the part that leaves appears resistive or dissipative, and the part that comes back periodically, that's called reactive. So when you have an impedance that looks reactive, that means energy is sloshing around. It's not going anywhere. So when we look at an antenna, we have this notion of radiation resistance. Since that propagating away part appears resistive, we represent it as a resistor. So that resistor, say in this example, is 36 ohms, which would be a monopole generally. And then we have some other resistance, which is the loss resistance. And that's a comparison that we make to try to understand energy or efficiency within an antenna. So if the loss resistance is high, a lot of the energy may go there, or we may not be able to transmit energy into the radiation resistance. If the loss resistance is low, generally we'll put a lot of energy into that radiation resistor. And you can think of it as a lumped resistor. That's a reasonable assumption for our purposes. And this is different from the feed point impedance. The feed point impedance may appear as both of those. There also likely be a reactive component. An interesting way to look at it is that speakers behave the same way. if you put a speaker in a vacuum, you're going to find out that it's purely reactive. It's going to be, except for like heating the cone up as it bends it a little bit to move it back and forth. But in order for speakers to have a resistive component, and this is separate from the wire, but let's say we had superconducting wires, and an example here. So the speakers actually does work on the air. So work is force times distance, or it's actually a dot product, but force times distance is good enough. And through the work energy theorem, we know that becomes kinetic energy that pushes the air. So if you put a speaker in a vacuum, you'll see it's reactive. You let the air back in, and you'll see that you have a resistive component. And that's the work you're doing on the air to get the energy from the cone to your ear. There's a bunch of other calculations you can do for dipoles. This is kind of boring stuff, and it's kind of pointless for most of what we care about. So we're not going to dive into this at all. But there are some estimates you can make and get a couple of quick calculatable formulas, for example, for short dipoles, and also gives us a number that we've all heard before of 72 ohms, which is the free space impedance of a infinitely long dipole. And even a half-wave dipole is close to that 72 ohms. But we can calculate the short ones using that 790 L over lambda. Now, pointing vectors, this is a really interesting thing. If you look at a circuit with just a battery and a resistor, where's the energy flowing? How does the energy get from the battery to the resistor? Is it inside the wires? Well, actually, it turns out probably not. I mean, we see electrons get bumped along the wire, but what seems to contain all of the energy transfer is this thing called the pointing vector, which is E cross H. That's a magnetic and electric field crossed in a vector cross product. And that represents energy flow. And there have actually been a couple of YouTube videos about this lately. Veritasium had one that caused a bit of controversy because it wasn't a complete explanation. But basically the wires are acting like waveguides or guides for the fields. And the fields are where the real energy transfer occurs. And so it's not just AC, this works for DC as well. Around a battery, there's an electric field there. And if you start current flowing, there'll be a magnetic field as well. And then you do that E cross H and you find out you can account for all the power except for power that's lost to real world elements. That's true in coax as well. The energy really is traveling in the fields. A waveguide is an example of that. So you have a waveguide, it's a hollow cavity conducting on the outside. Energy moves through there just fine. So that's an extreme example. So people, when they were trying to design new kinds of antennas, came up with this idea, well, if E cross H is the actual power or energy that's moving, and antennas do this thing where they get this E cross H thing going, what if we made an antenna that would just create an electric field and a magnetic field and get them to interact? And so they came up with these wild antenna designs. This was maybe about 25 years ago. There was a lot of thought about this. Well, we just use sort of a leaky capacitor and a leaky inductor, and we'll get those fields to interact, and we'll create a new kind of antenna. It'll be really compact. But sadly, it didn't work out. That it seems to be impossible to synthesize this pointing vector just using a couple of elements that don't look like what we now know as an antenna. So if we calculate where the radiation comes from, and this is a result of the impedance of free space, we find that most of the radiation in an antenna comes from where the current is the highest. And this is a guidepost. This is something you can use to evaluate an antenna, evaluate where the radiation is coming from. So this is going to tell us something about where we place the antenna, where we place things like loading coils, and how we put them next to structures. When we consider antennas, of course, pattern becomes something we worry about as well. If we have an isotropic radiator, which is not a real thing, we can't really build one of these, although we can build approximations to it. There's no preferred direction, but all the practical antennas in the world are anisotropic. In other words, they radiate preferably in one direction or the other. And if you take like a given power ratio of, I don't know, input power to power measured at that a little patch on the surface there, you get this 3D image. And this is what we call a pattern. And you can see a couple of examples there, one for a Yagi and one for a monopole. And as hams, we like to evaluate this in 2 dimensions. The azimuth, which is as if you're looking down on the antenna and sliced it horizontally. And you can kind of see the directionality of the antenna. So in this case, the Yagi is pointing all of its energy to the bottom of the screen here. And, you can see a couple of gain numbers on there on the plot. But those are very high gain numbers. It must be a very efficient antenna. But you can see that you get this sort of bubble of energy. If we go from the other orthogonal direction, we can see the elevation. And so we look to see how high the energy is coming up off of a horizontal plane there. So we slice it vertically. And that tells us something about what angle it's going to intercept something. And sometimes the horizon is the thing we care about, especially on HF, because that defines how far away the propagation will propagate generally. So a lot of DX will be down at very low angles to the horizon on the order of 3, 4, 7 degrees, something like that. Another parameter we may care about, and this is really true if you're operating on the 60-meter band, for example, in the US, is the effective radiated power. And this is the power that you get over an isotropic radiator. And now we have, and all of our antennas are not isotropic. So we go to the peak power direction and find out that power. And it's kind of like concentrating something. So, if you look at this plot, you can see that almost all of the energy is forced into this small area, and that makes it effectively more energy when it's compared to something that radiates equally in all directions. So you can think of it kind of like a light bulb, and you put a reflector around the light bulb, and then all of the stuff around, say, 3/4 of that gets pushed into the front. And so it faces most of the energy in one preferred direction, like a headlight or something like that. And terrain, of course, interacts with the pattern quite a bit in a very complicated way. The dirt is a dielectric, and it's also resistive. And so it does things like change phase and other characteristics, and that phase interacts with the phase of the antenna and can cause polarization, rotations, and can cause the antenna's pattern to shift quite dramatically based on things like the antenna height and how it impacts the terrain. And here's an example of just at 70 centimeters in the San Francisco Bay Area here. That's what it's frequency dependent. And here's what it looks like at 70 centimeters. And here's what it looks like at 2 meters. You can see really just different. So we have frequency component as well on top of just the interactions with the terrain. So as you can see, sighting an antenna can be a very complicated affair. Polarization matters a lot when it comes to antennas. The H field and the E field, the electric field direction, is generally what we classify as the polarization direction. So in the case of a horizontally polarized antenna, the electric field direction would be horizontal relative to the Earth. And this causes it to be a magnetic dominated phenomenon. And what we get from that is image currents. So the currents that are formed in above the dirt have a reverse current at the bottom of the dirt. And what this causes is destructive interference. The result is that the antenna pattern gets pushed higher in the sky. So when you have a low horizontally polarized antenna, what you get is patterns that tend to face up, which is why you like to have a tower with your Yagi. You want that thing well above the ground so that these image currents are much less of an effect. And you get all sorts of interesting interactions as you vary that distance, that height off the ground. You'll get lobes and peaks and different changes to the pattern. Most of that can be simulated. But the general rule of thumb is if you're going to operate with a horizontal antenna, you want to keep it up high. For the vertical polarization case, we get image charges. And the image charges form in the dirt just because we're also, moving charges around. Charges have effect on other charges. And so the image charges tend to, they just reverse it, but they don't curl around in the opposite direction like magnetic fields do. And so what happens is it actually pulls the pattern down. So if you have a vertical antenna and it's close to the ground and you're not dissipating a lot of that energy in the dirt, then you tend to pull that pattern nice down and low, which is why vertical antennas can be very good DX antennas. The only problem is they're often omnidirectional. Now you can make a directional vertical by putting a couple more elements in it, sort of like a half Yagi on the ground. And there's lots of directed arrays like that you can buy or build. But the idea is that you get this nice low angle of radiation, which can be very useful. And it even gets lower over highly conducting surfaces. I used the DX a lot driving over a bridge here in the San Francisco Bay Area. And as soon as you get to the bridge, you'd see a several dB increase in signal levels. Or if I was near a brackish pond, I'd see that as well. So going back to the dipole, let's take a look at what that pattern ends up looking like. So we get this toroidal pattern, which has nulls right in the direction of the wire. So it looks like a big donut wrapped around the wire. And this is, of course, affected by polarization. If you have a vertical dipole, for example, it won't interact much with the dirt if you can get it up so that it's not, just lying on the ground. If you turn it horizontally, though, the whole thing will squish upwards. And the nice thing about dipoles are they have a high radiation resistance, so it's pretty easy to feed them. It's similar to the impedance system, the system impedance of our transmitters. So it's pretty easy to match into these things. And it's pretty easy to feed them in the center, at least in the horizontal configuration. But again, when you have it horizontally, it's going to get all squished. Here's what it looks like in a few different angles. You've got the azimuth and elevation plots. So you can kind of see that, especially in the elevation plot, you can see that toroidal slice. And in the azimuth plane, you can see a fair amount of symmetry. Oh, now I'm going to get back to the practical stuff. Enough of this crazy theory crap. Let's look at the simple structures. Here's what we want. We want as hams, I believe, a fairly simple structure. That means it's easy to build or easy to put up. We'd like a really good pattern, and this depends on the dirt underneath things. And we'd like it maybe to have some gain in some directions. That could be useful. I have a hex beam here, and that gives me good front to back ratio. That's useful to me. And we'd like our losses minimized. And we'd like to couple this to the transmitter in a reasonably efficient way. Let's dive into a little bit of that. For ham radio and this pattern and elevation stuff, the idea here is that we want station-to-station comms, right? We want to create this circuit between us and DX or the friend you're talking to or whatever. VHF is sort of an easier problem to look at because it's mostly line of sight. And that has to do with the fact that it doesn't interact with the ionosphere very much. But for HF, we want to talk more about this high and low angle stuff. So if we want a really long DX contact far away, we're going to want a low angle just because that incident wave in the ionosphere will bend just enough to get it back down thousands of miles out, and off it goes so we can get good F-layer propagation. But that, again, is frequency dependent. And then the directionality. If you're working a North American contest and you're in the middle of the country, you may not want directionality at all. But here on the West Coast, when we do field day, for example, we will use gain antennas. So my club uses a bunch of Yagis pointed east. and then we can rotate to the northeast, and then we can cover everything. But that's not always what you want.
Can
Here's an
I ask you
example.
one question?
Sure, absolutely.
Yes, about the elevation of the propagation. Will it
Mhm.
be possible I will need to make my directional antenna in elevation of 20, 30, or 40 degrees, depending from what elevation the propagation is coming to my antenna?
Yeah, absolutely. Well, it will have an effect. So it depends on what you're trying to do. But, if you want to work the really far away DX, then you're going to want to have that pattern concentrate energy down below 10 degrees. So you want to keep that in mind when you do your designs.
Yes. So it is not wrong to think that the Yagi antenna need also not directional left and right, but also elevated up and down.
You could do that, especially if you want to. I mean, that's a hard thing to do, but if you have a crank up tower, you can do that. And the pattern will shift accordingly. So as you take a Yagi down lower, the pattern's going to shift up and you'll get more local communication.
Yeah. Okay, sorry, thank you.
No problem at all. Here's an example up here now where you can see the difference between horizontal and vertical polarization on the same antenna. Quads are really easy to switch between horizontal and vertical polarization just by where you feed them. So you could, with a couple of relays, just make a change like this. And the blue one is the horizontally fed, the horizontal polarization, and the black one is the vertical polarization. You can see that in the vertical polarization, you get a lot more energy concentrated down low for overall. But in the horizontal configuration, you get the split lobe. And I don't know if these things are actually perfectly overlaid on one another, but you do get the split lobe. So some of this energy is going up into the sky, probably not refracting back down to the Earth's surface. So not useful to us for what we do. Aperture is something that's in the commercial world talked about a lot, but in the ham world, we don't talk about it that much. And it represents the effective capture area of an antenna. So you can think of an antenna as being a patch on a big sphere, trying to capture some energy that came from the center of the sphere. So it's how well we can capture some size patch. We think of this as gain, antenna gain, but it's not. I think it's useful in your mind to think about the idea of an aperture. How much of that energy, there's a wavefront coming by your house, and how much of that energy are you able to grab out of the ether there and force it down into your receiver. And there's a really interesting and easy equation to work with called the Friis transmission equation. And this tells you also a bit about how effectively you're going to get energy from point A to point B. When we've set up stations to do QSO parties where we have a lot of transmitters close to one another and a lot of operators, we use the Friis transmission equation to figure out how much interstation interference we're going to have to deal with. And so we orient the antennas so that their nulls are facing each other and that kind of thing. And the Friis transmission equation tells us a bit about how much energy we're going to have to deal with there from the other transmitter. Another interesting characteristic of antennas is the Q, and Q has to do with how tightly the antenna's characteristics are bounded within a certain frequency slice. And low Q antennas are usable across wide bands. This becomes really important, for example, on 80 meters. So the 80-meter antenna has to cover a fairly wide swath of frequency. And so you generally want a low Q antenna for that. And then high Q antennas can usually be made small, and they only cover a tiny bit of the spectrum. And there's this thing called the Chu-Harrington limit, which has not been proven, but this has been experimentally shown, that the Q, or the usable bandwidth of an antenna, is proportional to a sphere that encloses all of the antenna elements, which is kind of interesting. properly. And so you can see this in action when you have, for example, a tuned magnetic loop, one of those really small magnetic loops. When you tune those things up, you'll find that they only operate well over a very small bandwidth segment. And part of that you can rationalize with the Chu-Harrington limit, because the sphere that encloses them is fairly small. And of course, that's proportional to the wavelength. So if you have an 80-meter magnetic loop, it might not even give you an entire segment to transmit SSB. So it might be very, very narrow. So there's no free lunch there. Loss is a characteristic we have to think about. And I think of it a lot in terms of heat, because that's where most of the loss goes. So we heat the dirt, we heat some wire, we heat a coil, or we're heating the feed line. That's not everything, but that's the majority. That's mostly what you care about. And one thing that's interesting that I think a lot of people ignore is, I'm sure you've seen on a portable antenna, one of these taps like this, where you have a coil and a clip and a wire. And the clip goes somewhere on the coil, and that allows you to match the antenna to your transmitter. But the thing you have to be aware of is that there's circulating currents here. So when you short out that part of the coil, that doesn't mean that part of the coil is gone. It's still there. It's still interacting with the fields. And so currents flow around in a circle around the remaining part of that coil and the shorting wire, and you actually lose a non-trivial amount of energy there. So other antennas have sleeves like that, or they can leave that open at the top, and then you don't get those circulating currents, and it's much more efficient.
Kristen?
Yeah.
Hi, sorry, I can't see the hand raise thing on my view here, but so I had to jump in. What about rain and mist, relative to heating the ground and all those other things? How much would rain and mist and other forms of water in the air absorb?
So for rain or any liquid to have an effect, there has to be an ionic component. For example, distilled water doesn't really conduct. So if you have salts, which are usually ionic bonds, the ionic bonded materials, the water will activate them, and then they'll be mobile, and then they'll start affecting things. So if you're over, like salty dirt, or you're in salty mist, that's going to affect things considerably.
Okay, that makes sense. So it has to be a conductive thing.
That's right. The water itself doesn't do much. Water's barely polar. It's mostly a nonpolar molecule. So where does this leave us? What do we want out of AM radio? Well, we want to talk to another station with the strongest signal we can muster. We want a reasonable structure that we can actually build. That'd be nice. And an easy thing to interface to. And I have a whole nother talk about SWR and how that's just a way to make your transmitter happy more than anything else. There are some losses involved, but I just wanted to mention that because one of the things you'll encounter here, and I'm going to give short shrift to in this talk, is the SWR part of this. But I will mention it. So from those values, let's dig out some principles. We want to optimize the pattern, and that doesn't necessarily making it narrow. Doesn't necessarily mean making it narrow. We have to figure out what we want to do. Like we have that omnidirectional requirement for contesting in the middle of the US or the middle of Europe. We want NVIS, in which case we change what we're after, or we want a DX. Then we want those low angles of radiation. In general, we want to increase the radiation resistance if possible, because that gives us lower loss resistance. Or puts less power into the effective loss resistance. So if we get a high radiation resistance, it's generally a good thing. We want to choose our aperture gain, and that sort of interacts with the pattern and figure out what we want out of that. And then something you can build. A lot of antennas, for example, you could make a 20-meter J-pole, but it's kind of hard to deploy a 20-meter J-pole. It's very long and needs to have that matching segment mostly free of other structures because it's kind of sensitive. So you have to figure out what you can reasonably put in your yard or actually build in practice. So this all gives us a lens to look at things. So with these, we can look at a few antennas, and we're going to do that and see what you get and what you don't get out of that. And the thing that I like to emphasize here is that don't go for perfect, because you'll never get there. Just get one that's optimal for the things you're most interested in, and I think you'll be a happy camper. And as I mentioned earlier, SWR, do we really care about that? Yes and no. Basically, our transmitters are designed mostly for 50 ohms these days, and we're trying to make them happy so that they can couple the energy from in there out to somewhere else. Efficiency is mostly a matter of how much power do we burn up in coax losses, which actually turns out to be not as bad as you might think, but you can calculate it, figure out if it's acceptable to you. And most importantly, SWR is what I call a degenerate metric. In other words, it tells you something, but it sure doesn't tell you everything. And for example, a 3-to-1 SWR, as it says on the slide, has an infinite number of solutions, and there's two of them for your amusement, 150 ohms and 16 ohms, both give you 3-to-1 SWR. So as it told you something, maybe, maybe not. If you look on the Smith chart, you get this whole circle of impedance values that on a, say, 50 ohm system, that would give you a 3-to-1 match. And
Kristen?
Yeah.
Sorry, not to trigger a long conversation, because I know that's a whole nother presentation, but why is it you think that so many people get so confused about what SWR is, what it means, and what they should do with it? What triggers all that confusion?
I think it's because it's an easy thing to latch onto. They sell meters, and you can look at it on the meter and you can say, oh, yeah, right, not 1-to-1, therefore bad. And there have been a lot of erroneous explanations out on the web and in books and things like that as well. So I kind of think it's just one of those things where, and I actually work on scoring systems that have to do with a lot of nonlinear metrics and things like that in my day job. And I find that people just latch on to certain things because they're just in front of their eyeballs. I don't know if that's a good answer, but.
No, I think you're probably right. It's one of those things that seems like it's never going to finally be clear to everybody.
Yeah, I agree. Which is why I did the other talk, because I just, it bugs me too. But anyway, if you understand the Smith chart, you know what I'm talking about. There's a whole circle of values that are all the same SWR, and matching can be difficult. And there are unmatchable loads and sources. And so, if you can get it down to a place where the transmitter's transistors are pretty happy, or the tubes or whatever, then leave it be. Is my advice. So let's go through a couple of examples, and I'll just make a few comments about the characteristics as I see them, and then we can call it a day here. And your favorite antenna may not be in here, but it's probably like one of these. So we start with the plain old monopole, which is a dipole that has the other half severed and replaced with a conducting plane. And it halves the radiation resistance down to 36 ohms in the ideal case. They're really simple. They don't need a lot of height. That was me in, I think, Vancouver, maybe, playing around in a park. They are fairly low Q as long as they're full length. But you have a lot of loss to the dirt if you're not careful, which is why I tend to use a lot of radials on the ground, minimum 16, and have this nice omnidirectional azimuthal pattern. So if you're just playing around, they're great for that. But do remember that when you shorten them, the Q goes way up. And here's the shortened version. And what we do with the shortened version is we put a coil somewhere in the middle that's sort of like a missing piece of the antenna, although it's a little more complicated than that. You may get lower gain. It depends on a lot of things, but you'll certainly get lower radiation resistance. Again, it has many of the characteristics that a monopole has, a full-size monopole. But the Q starts going up. And the thing to really remember when you do this is that that top half of the antenna above the coil is mostly like a matching section. It's just kind of getting the thing to be the right impedance for the lower half, which is where almost all the radiation occurs. So all of that real work of the antenna is below the coil. And you can see this on mobile installations too. For a while, I had a mobile installation with the coil low, and then I just pushed it up high, and wow, what a difference. And you'll see the feed point impedance and the radiation resistance go up significantly when you do that. And and for portable antennas, it makes a big difference too. I have this PAC 12. I don't know if they still sell it, but it's a very lightweight portable antenna. And it had an approximately 18-inch lower section below the coils. And I just immediately went out and bought 3 more sections. And so I pushed that coil up really high and then just used the top finger, which is one of these telescoping deals, to just match it up so that it makes the transmitter happy. But the antenna performs so much better when you have it longer section beneath the coil there. And you can do it horizontally too, as you can see here, and that's got a couple of capacity hats on it. And the capacity hat is a clue that this is more of a matching deal on the other side of the coil.
Another quick question.
Sure.
Is radiation resistance, given a specific frequency and a specific antenna, is radiation resistance directly proportional to signal strength at a given distance?
Not exactly, because it depends on what your feed point impedance is, what your transmitter wants to couple to. So if you have a radiation resistance that matches well with the transmitter, then it can dump the most energy into that radiation resistor. Think of it just like a resistor, and a voltage source. And how can you get the most power in there? But the voltage source doesn't drive all resistances equally. So it's a little more complicated than that, but just think of it like a resistor. And it looks like John N6UOP has a question.
Yes, on your previous example of the vertical antenna, you added additional sections to the lower part of the antenna. You said that it improved it, a qualitative answer, but what do you use quantitatively to analyze that to show that that's a better match or better performing antenna?
The thing that really tells you the answer to that is a field strength meter. So you get a field strength meter and you get a bit of a distance away, so you're not exactly in the near field, and you measure it that way, and that's the best way to know quantitatively what's going on.
I see. I noticed you didn't mention SWR on that, which everybody uses to look at their antenna performance.
Yeah, that's complicated. And what happens, right, and SWR doesn't necessarily indicate antenna performance. Field strength is the real answer.
Gotcha.
And what you'll see with these shortened antennas too is that if you don't have enough radials, they'll tend to match better because you get a lot of loss resistance. If you have a shortened vertical with a lot of radials, you'll find it matches pretty poorly. And that's because that feed point impedance is going way, way down because the radiation resistance is low and the loss resistance is low. Make sense?
Thank you. Yes.
Sure. So horizontal Yagis, they have some really great gain and front to back ratio and those kinds of things. So you're controlling the pattern pretty carefully with an antenna like this. They tend to have pretty low radiation resistance and pretty low feed point impedance. And we compensate for that with things like gamma matches or some similar matching thing. But so we can couple it better. But the loss resistance is generally low because we tend to put them up high. We put them up high so we can get a better pattern. But they're big and heavy, especially in HF. And they have sort of a medium Q to high Q. And this has to do not only with the impedance shifting around, but actually the pattern shifting around. So the element links are really important and they're frequency related. And as you move the frequency around, you'll get a lot of variation in the pattern, which is why the you know, the what do you call it? The step IR is an interesting design, even though mechanically they have issues, but it allows you to fine tune that element length and get that to match the frequency pretty well. The problem is you can't vary the boom length. If you could vary the boom length, that would be even better. But you can get, you know, really good effective radiated power out of these things. Directional patterns are great for DXing when you have to point in a particular direction, obviously. Now, the G5RV, this is like everybody's favorite antenna or something. A lot of people swear by these things, but they're really bizarro antennas. They give you all kinds of weird patterns. And you can see here, it's a little bit tiny on the screen, the different kind of patterns you get with the G5RV, even at 20 meters. You can see this sort of flower petal-like pattern. And as you go up in frequency, it tends to get more complicated. And what you've got here basically is two wires and a matching network that tries to make sure that they're not anti-resonant at any particular frequency. And then you use an antenna match to try and get the thing to a place where you can drive it. Or maybe you cover a particular frequency where it's drivable with a 50 ohm transmitter. The Q is kind of all over the place. So G5RV will work. It's nothing here that says it won't work, but you're going to get a lot of different characteristics as you move up and down the bands. And they may be not the characteristics you want, or maybe the ones you want. I don't know. But as you can see, it stabilizes too as you get lower in frequency. But at the higher frequencies, you get a lot more interactions in the near fields. And that's because, you know, the wavelength is closer to the size of the antenna.
So a G5RV is a dipole fed by a section of ladder line?
Yeah, it's not, yeah, you could call it that. Yeah. I mean, we generally associate a dipole with something that's close to a frequency that matches the length, but yeah, it's just two wires and a ladder line. And the ladder line is there to try and avoid places where it would be really tough to match. Large loops, they make these nice bulbous patterns like this. They have nice high radiation resistance. They're hard to get them to work, certainly if they're vertical, they're hard to deploy. Horizontal loops have other characteristics. Some of them look a lot like those you know, cubical quad antennas is sort of an example of that. But the fat toroidal pattern, that's the characteristic you get from them, which is nice. They're just hard to deploy. Now here's the magnetic loop. I'm a fan of these antennas. They're nice for portable operation. They're really good. But the thing you have to keep in mind is they do have a sharp null in the pattern at certain frequencies. And the thing that is really the most important characteristic is the very, very low radiation resistance. And this means that the loss resistances tend to dominate. So the connectors where you connect them from one place to the into the, say, capacitor in the middle there, that's really important. And the Alex loop, if you have one of those, it uses plated coax connectors to try and minimize that resistance. If you want to do it but be really efficient, you have to you know, use silver solder or something like that to get the thing to couple really well into the capacitor. And you want the capacitor to not have resistive losses as well. But they're really interesting antennas. I think of it as like ringing a bell. You know, you have that little exciter loop, and the antenna is like a tuned circuit, and you just hit it really hard, and then it oscillates really well at its natural frequency and radiates really well. But again, that resistance will really catch up with you quickly. And as I mentioned earlier with the Chu-Harrington limit, the smaller they are relative to the wavelength, the narrower the bandwidth of the antenna is going to be. So at the really low frequencies, they become almost unusable unless they're really big. Half-wave NFEDs. This is an interesting antenna. It's kind of like a dipole, and it has many of the antenna characteristics of the dipole, but the feeding is where the problem may occur. You know, you have to have this transformer to increase the voltage a lot so that you can feed it at the end. You can think of yourself as sort of sliding along the dipole and seeing the different impedances as you go. And so by the time you get to the end, you're at a fairly low current and fairly high voltage. And that can make the building an efficient transformer a bit of a problem. So you want to make sure that you have an efficient magnetics in that transformer in order to make that work. But they can work very well. Just try not to get things near the end of that wire. And the transformer is what gets you the matching and the impedance that you want. But the radiation resistance is a lot like that of a horizontal Yagi. So they're kind of nice from that perspective. And here's another fan favorite, the off-center fed dipole. People ascribe all sorts of magic characteristics to the antennas, but just like the G5RV, it's just another pair of wires and might even be like a real dipole. But you've slid the feed point off to some other place that's not the middle. But it's still going to act just like a dipole or a doublet, if you will. And you just have a different feed point impedance and different resonant and anti-resonant characteristics at different frequencies. So what it's trying to do is move around that feed point impedance so it doesn't bump into anything bad at ham bands. But there's nothing really special about the OCF dipole, especially if the feed point is well decoupled from the antenna elements.
What do you think about the Wyndham variants where they isolate a section of the feed line?
Yeah, well, you want to isolate the feed line because it has to, otherwise it's part of the antenna system. So you decide how much.
Like I have modified Wyndham's antennas in my yard, and each of them has a coax isolator 10 feet below the feed point.
Is that isolated with what?
Probably isolated either with chokes. Chokes, probably. I don't think it's a transfer.
Yeah. That's the usual thing. So the part that's above the ferrite beads, that's part of the antenna system.
Right.
And everything below it is now probably not much part of the antenna system. So, that'll give you a slight tweak to the pattern more than anything else. But it's still going to be very dipole-like.
I think one of the things I heard is that it also gives you both horizontal and vertical polarization.
A little bit. Whether that's really significant or not, I don't know. Depends on the length relative to the wavelength. So if it's really short, probably not. But yeah, I mean, you can tweak all kinds of things like that. And, you've got now a 3-element antenna. You could also make that out of wire. And then the J-pole, which is a really interesting from a electromagnetic standpoint antenna. Basically, it's an end-fed dipole, sort of, with a transmission line transformer feeding it, and a short at the end. And so what the impedance is nailed down at the end, and then you move the feed point up to where it's sort of 50 ohms-ish, a little bit away from that. And that's, of course, very much wavelength dependent. And then that gets transformed into the high voltage, low current that drives the end-fed half-wave dipole, more or less, except that all those fields interact. So the transmission line transformer is not off by itself. It's actually in the field of the end-fed half-wave. And so that affects the pattern too. So it's a little bit of a complicated thing to measure. You can see an elevation slice at the bottom here, and the dipole's the red one, and the J-pole is the green one, and you can see that it pushes the pattern up just a bit. So that's nice. You're kind of getting a vertical dipole out of the deal, and still get that nice vertical omnidirectional azimuth pattern, which is nice. They're fun antennas. You can make them out of twin lead too. And then there's the isotron. Has anybody ever seen one of these? So the claim here is that we're doing pointing synthesis. However, it doesn't really work because nobody can do pointing synthesis. What it ends up being is a reactive termination to a piece of coax, and the coax is doing all the radiation. So if you choked that coax up towards the top, you might find it's really hard to match the thing. And the energy's not going anywhere. So a lot of these antennas that claim to be one thing or another are not variations on the more classic designs are not really doing anything useful, or they're doing it in a way that's not obvious. So going back over this, what matters most to us is the communication. We can decide on the pattern based on what kind of communication we want to do. Efficiency is generally important across all of these antennas. We want to look at the radiation resistance, the loss resistance, the gain of the antenna may be important as to how much we want to concentrate energy. And then convenience. Sometimes you want to carry it in a backpack. Sometimes you want to be able to build it yourself and take it to the park. And sometimes you want it to be a permanent structure on your property. All of that matters as to what you choose. And then the transmission part, which is the feed point impedance, is probably pretty important. Can you actually match it to the transmitter and make the transmitter happy? And a little bit of concern about how much loss is in the coax. At HF, it's not as bad as you think. Just run the calculations.
Looking
so if you're interested in
I'm sorry. Looking at those two pictures of the antennas, the Yagi versus the mag loop. We've talked a lot about transmission, but what about receive? That Yagi to me seems like it would receive better than the mag loop, even though
there's a lot of symmetry between transmitting and receiving, and modern receivers are so good that you can get down to these noise floors are really low. So I don't think there's too much concern about that. You have more trouble transmitting, trying to get that energy out there and into the air. But the receivers are just amazing these days. Some of the new SDRs are even pretty good. So receiving is not as much of an issue. And that's why, you can get one of these shielded magnetic loops that have really horrible characteristics for transmitting, but you can put a really good LNA on there and then use those purely for receiving and cut out some noise in the process because they don't respond to electric fields very well.
Christine?
Yeah.
I have one silly question I am asked a lot here in local, and so I don't have an answer for it. And I understand. Okay, I have antenna in mind. Let's go and say I have a big coil and small antenna like hamstick for 160 meter. I transmit 1 kilowatt into it. I have a camera with a heating meter. I can see that the ground is not getting warm at all. The coax cable is not warm, and the antenna is completely cold. So where do my power go? I know
That's a great
is
question.
99% lost, but to where?
Yeah, that's a really great question. If the antenna is not, it's almost certainly going heat somewhere.
But where?
The question, I don't know. Have you measured the vector with a vector power meter? Measured the power going out to the antenna?
Yes, I have done that, and that surprised me also. I know it is terrible antenna, but where I'm told, well, of course, the power is not. It goes somewhere, but the question is, where is it going? If it's not going to heat, it must, and I'm told it go to ground, but the ground is not hot. I mean, even not 5 degrees warmer than the rest of it. And I use 1 kilowatt just to see the heat. So I will see definitely that 900 watt is going into heat, but to where?
Yeah, I don't know, have an answer for you. It's going.
Okay, then I'm
maybe
not
it's
so bad.
widely dispersed.
That's exactly I say also to my student. I have no idea.
Yeah, sorry. Yeah, I mean maybe. Well, you probably have to do a wider analysis. Maybe it's widely dissipated. I just don't know though.
Okay.
So if you want to learn more about this, the ARRL antenna book is a really great resource for practical stuff. Lots of good suggestions for antenna geometries and things you can build in there. Wikipedia has some of the more technical details, but it tends to be obtuse. So you really have to dig in there to find out what they're really talking about. They put a lot of jargon and mathematical symbols in there to, I don't know, make it seem more obscure. There's some good antenna theory books out there. I happen to have a copy of this particular one here, but there's lots of others that can help you understand the theory part. But then I say, use your common sense. You know a few things now about what matters most, and apply those to your antenna systems. So I'll take some questions if there are any additional ones.
Bruce, you're up.
Is there a way we could get access to your presentation?
Yeah, if somebody sends me a follow-up email, I'll send you links.
Thank you, Bob.
Bruce, it's being recorded.
Oh, you got that too. I have the slides though.
Yeah, I like having the slides themselves for reference. Easier to look up.
Okay.
Well, me too.
Kristen, thanks for the presentation. Very interesting. Could you comment at all on log periodic antennas and why they seem to be very, very favoured by defence people and tops of embassies and things like that?
Yeah. So the reason that they're favored is that they're frequency agile. You can kind of think of them as two-element Yagis where the two elements kind of slide along the boom at different frequencies. So they get activated by the fact that they happen to match the wavelength as they go. And you see that also for HF aeronautical. It's another popular use.
Yeah. Yeah, I have a horizontal loop, an 80-meter horizontal loop that's about 12 meters off the ground, so it doesn't get too many ground effects on 40 and up. It works really well on 80, 40, and 20.
I'll bet it does, yeah.
What's the best way to learn how to use, I'm sorry, were you done?
Yeah.
I was going to ask, what's the best way to learn how to use ESNEC?
Oh man, I don't know about that particular implementation. NEC itself is a really an ancient Fortran program, but I'm sure there are guides out there on the internet, and there are much better antenna solvers because that's NEC 2, I think, or NEC 3 maybe. But there's been a lot of work done since then. But sadly, most of it's commercial products that you have to pay through the nose for.
You said you showed the monopole with all your radials that you got on the ground. Would you benefit from raising those off the ground and having them come at a sort of 45-degree angle or something? It always seems to work for me. Yeah,
absolutely. If you are able to do that, that's generally a win because otherwise, you're warming the dirt. Although, given the previous comment, who knows? But and also, if you get them completely elevated, then you can use fewer of them. And I think Motorola decided that 2 was actually adequate if they're sufficiently elevated.
Right.
So, but then they have to be resonant as well.
Mm-hmm. Yeah. I wondered if Harry's thing is because he's in Iceland and it's so cold anyway. He's got a natural cooling effect when he tries to measure the temperatures.
Yeah, I don't know. Now I'm really curious about this. So I'm going to try and see if I can find any papers or studies on that topic.
He can't see anything hot because it's all cold.
Right. The IR camera is not working right.
That's right.
The only thing I found out is it was summer, not so cold, and I was testing on SSB with a high power, and she can hear my voice from the coil of the antenna when she was fixing the flowers. And that is the only thing I found out, that something I was not expecting, that the coil was moving in some direction, that it made air voice. And I never heard about antenna that you can hear the SSB singing from the antenna, but that is what it happened was with that 160-meter hamstick antenna that I tuned exactly to standing wave 1.1, so it will be 50 ohm to my coax. And I was trying to find out why is that antenna so terrible working. I'm all in satellites and no elevation of radio waves, and I was just wondering, it do not go straight up, and where is the power going if it's not disappearing somewhere?
Yeah, well, I guess some of it's going into mechanical energy, but that is impressive. And, those forces are real out there, the magnetic and electric forces.
Yeah, but I know that I was speaking to one big station in Finland, and I am in Iceland, and he told me he pointed this big Yagi antenna 20 degrees up to get my maximum signal. And I thought it was quite interesting. That's I do with satellite dishes. And I never heard about beam that is elevated up and down. So that is why I'm telling all the main top stations, why do you point your beam horizontally completely? I will think that 50% of the power will go to the ground and the other 50% will get in some kind of elevation up in the air.
Ari,
Yeah,
was that a
you could-
vertical hamstick or did you use a hamstick dipole?
It was a vertical and the ground was perfect. It was just a metal roof, and I was trying to find if there was any heat on the metal on the ground. And even the coax was heavy duty and very short. And I was checking if the heat go to the coax. And well, I could not find the way.
Yeah, I would
Only
expect
thing,
that the dirt itself would get warm, if anything.
yeah. So the only thing I was surprising was that the coil was moving, so it made sound.
Yeah, that's interesting. Well, if you ever get a chance to perform the experiment again, maybe just use a dead carrier and just leave it on for a minute and see what happens if your amplifier will tolerate that.
Yep. I have a problem. I got my amplifier from US, and he is now broken, and I can't export him to US. The new regulation in USA, it is forbidden.
Oh, no, that's a pain.
Exactly, and now I'm thinking to fly with them to US. I can do that.
Yeah, well, it's just not super heavy. You could do it.
No, well, he is quite heavy, and that is the point, and he's under warranty. Otherwise, I will fix him.
Yeah.
But that's different thing. So, I have no problem to find 1 kilowatt amplifiers that can handle 160 meter for 1 minute. That is not a problem.
That might, a good solid carrier pumping that energy constantly might
Yes.
give you a more measurable signal.
I'm
heat
using
signal,
the power just so I will be more clear where it is going. I mean, it will go to heat, but where?
Yeah. Well, what I'm saying is just, since you want to integrate more of that power over time, just have a steady carrier and key down and then watch it with the IR camera.
So,
Would be a
example,
clean
one other
experiment.
thing, one other thing I'm telling my locals over here is that the gain is not important. It's a question where do you need to get your signal into. Example,
Really?
if you have a quart wave vertical, it is best for satellite. 5/8 antenna that have more gain, but it can't reach satellite over your head. And I'm talking about VHF antenna. Then I have 15 dB gain antenna vertical, and he can only hear the satellite when he is in a low elevation. When the elevation go higher, the satellite will disappear. So the antenna that have 0 dB gain, I'm talking about quart wave antenna, I can hear the satellite all the way from when it arrive over the horizon all the way to go down the other side. So the low dB gain can make me better signal. It's possible.
Yeah, absolutely. And, when I give talks about antennas, I always emphasize that there is no best. It's what you want to do. And then you just optimize for efficiency.
The gain is just a question if you like to narrow all your power into one direction, and then question is to where.
Absolutely. Yeah.
And for
Kristen,
me, yes.
You mentioned, sorry, Ari, you mentioned receive antennas or antennas for reception only briefly, just at the end there. I do use beverage antennas sometimes to, particularly for low bands like 160 and 80. And obviously very low noise and a better signal to noise ratio. But when people ask me to explain, I mean, I know how they work, but when people ask me to explain how it works, because it's just like in the hedge and not far off the ground and stuff, but they don't sort of, and it works end on rather than off the sides like most bits of wire. I just find it really hard to explain. So I wondered if you had a really easy way to explain beverage to somebody.
Well, I mean, you could just say, well, it just has this really narrow pattern. You can think of that
Right.
as ERP, right?
Yeah.
And then there's this, great asymmetry between transmitters and receivers. Receivers are really good at looking at weak signals. So you can have an inefficient but narrow antenna. And
Right.
and remember also, when it's narrow like that, you can think of the noise as being isotropic. It's coming from everywhere. But when you have that narrow aperture, you get a lot less noise.
Yeah. Yeah, that's really good. Yeah. Thanks.
Any other questions? Well, thank you, Kristen, for insightful and engaging presentation. We really appreciate you sharing your expertise and experiences with us today. I'm sure everyone gained some valuable ideas to apply on their own stations.
It was my pleasure. Anytime.
Thanks, Christian.
Thank you, Kristen.
Yeah.
Thank you very much.
My pleasure.